the periodic table. But the periodic table, more than anything, really just helps you be able to anticipate and identify different trends and or behaviors in our structure of an element or an atom. In order to understand how the periodic table is even laid out, though, we need to review how an atom is structured. So an atom, you've got 3 subatomic particles: nucleus, protons, neutrons. The electrons float around outside of the nucleus. The nucleus, because it's protons, which are positively charged, and neutrons, which are neutrally charged. The nucleus itself is overall positively charged, whereas electrons, which are spinning around the nucleus, are all negatively charged. So the positive charge of the nucleus is pulling in the negative charge of the electrons, and that is an attractive force. That is what keeps the electrons from just flying off into outer space, from actually staying really close to the nucleus of the atom. In contrast to protons and electrons being an attractive force, you also have all of the other electrons that are spinning around at the exact same time as that one electron. And all of those other electrons are creating a repulsive force, or a force that's pushing things against each other. And so that ends up creating some type of a very well-structured, layered concept where you have orbitals, shells, and subshells in which the electrons actually can move, where there's a balance between the attractive forces from the protons that they're feeling and the repulsive forces they're feeling from every single other electron above, below, beside, all of the things around it. Let's say you have 1 proton and 1 electron. There's no repulsive forces from other electrons because there's only 1 electron, so it's going to be pretty close to each other. Now let's add another electron and another proton to that. So now if we have another electron, these 2 electrons now are going to have to start spinning opposite one another. They're never going to get too close and never going to be too far from each other. They're always going to be basically 180 degrees away from each other at all times. So they're never going to touch. That's their repulsive force. They're both still being pulled to the center by the protons, but it's being pulled in balance to what's being repelled from the other electron. Now, that creates 1 orbit. Both of those electrons, they can only be 180 degrees from each other, so you can only have 2 electrons that ever exist in the same orbit at the same time, simply because they have to be as far from each other as they could possibly be. Whether that's this direction, this direction, this direction, all the different angles and dimensions that you can have, they have to be as far away from each other as they can get. So you can only have 2 electrons in 1 orbit. However, when it's really small, you only have 1 orbit. As you get bigger and bigger and further away, those electrons are going to start to want to move in other directions. And as those electrons start to move in other directions, instead of just making a circle, they're going to start to now make like ellipses and be in a bunch of different directions. And then you can create more orbitals that are in the same subshell. So although only 2 electrons in 1 orbit for the S subshell, you can have 6 electrons. You've got 3 different orbits when you get the P subshell. So you can have 6 different electrons because there's 3 different orbits and there are 2 electrons in each orbit. So you can have up to 6 electrons within a P shell. And the shape of the P shell looks like there are 3 orbits. The shape of an S shell looks like it has 1 orbit, which is the sphere. When you have the D shells, you can have 10. So they have 5 different orbits with 2 electrons in each orbit to make 10 electrons to make up the D. The big thing to know is that there are 2 electrons in 1 orbit, at least 2 electrons in each subshell. You can have 1 shell, that's your layer 1, and that's only going to have S. Let's talk layer shell 2. So shell 2, you're going to have S and you're going to have P. So those electrons are either going to be in an S orbit or the P, one of the P orbits. There are 3 different orbits in the P subshell. The shells are correlated to the periods that you have on the periodic table. Periodic table. So after 1 period, it repeats itself. 1 period repeats itself. So if you look at all elements that are in the same column, because we talked about the period repeats itself, all of those elements in one column are going to have the same number of electrons in the outermost shell. The way you can tell how many electrons are present in the outermost shell is based on the number of the column. That is also known as the group number. Most of the elements that we will discuss are groups 1, 2, and then 13, 14, 15, 16, 17, and 18. The D block, where it's 3 through 12, when they're talking about electrons in the outermost shell, the D block is not going to follow that same pattern of up to 8. It's going to have more than that. The biggest thing to note is that it's way easier to fill an S shell or a P shell than to fill a D shell. So your energy-wise, it is going to be preferable to fill an S shell or a P shell, not fill a D shell. So you may have seen that arrow thing where you have 1s, 2s, what does any of that have to do with anything? When we talk about energy, where I was talking about like the forces that are bringing things attracted to each other or pulling them away from each other, that all is another form of energy. And so there's a certain amount of energy that has to be input to like overcome whatever energy is attracting the electron to the nucleus if you're trying to get rid of the electron. Getting rid of an electron creates a charged atom, which is also known as an ion. So the energy required to get rid of an electron and create a charged atom is called the ionization energy. As you get further from the nucleus, there's going to be a lot less of a force attracting those electrons. So there's going to be a lot less of an energy needed to input to get one of those electrons gone when you're further down on the periodic table, when you have more shells. Whereas when you're higher up on the periodic table, you have fewer shells, you're way closer to the nucleus, and it's going to take a lot more energy to get rid of one of those electrons. So the ionization energy increases going up on the periodic table. Similarly, when we're talking about creating an orbit that is stable, the most stable is 8. And so the most energy is going to be required to remove an electron when it is on the far right side, because there are so many more electrons there. It's far more stable. Whereas on the left side, there's very few electrons. And so going back to the whole periodic, meaning it repeats, it's much easier for it to remove 2 electrons and get to stable than to add 6 new electrons to try and get to stable. So the highest ionization energy is on the top right of the periodic table. Another concept that relates to trends on the periodic table is the electron affinity or electronegativity. Affinity is like how much you like something or how likely something is to bind to something else. I have an affinity towards my best friend, otherwise known as electronegativity, because when you add an electron and you don't change the number of protons, you're making an atom become more negative. So adding an electron, making it negative, is the electronegativity. So the electron affinity, the likelihood of adding the electron, and the likelihood of adding the electron and making the atom negative are similar concepts with the same trend. The electron affinity and electronegativity trends on the periodic table, if it takes a lot of energy to remove that electron, then it's not going to take a lot of energy to add that electron. If it doesn't take very much energy to add it, then it's going to be more likely to occur. If it's going to take you 2 minutes to do something versus 15 minutes to do something, you'd rather do it in 2 minutes and 15 minutes. So something that is easier is going to be more likely to occur, have a higher increased affinity. So something that has a high ionization energy also has a high electron affinity or a high electronegativity. Those are going to increase going up on the periodic table, and it's also going to increase going to the right on the periodic table. In complete contrast to both ionization energy and electronegativity, the atomic radius is literally just how far the distance is from the nucleus to the furthest out or the outermost electron. And as you increase the number of electrons, they're going to compact towards each other and shrink until you get to the next shell. And then it's going to expand again. And then it's going to contract a little bit, and then it's going to expand. So the atomic radius is higher on the left side of the periodic table than on the right side of the periodic table. At the same time, the atomic radius increases as you're going down on the periodic table. So the atomic radius increases going down and to the left on the periodic table. So atomic radius is direct contrast to electron affinity and ionization energy when talking about trends on the periodic table.